time. I can introduce you, Greg. Are you ready?
Yes.
Let's see everything works. So welcome back, everyone. Today we have Gregg Musiker, and he's going to tell us about double dimer covers on snake graphs from square cluster expansion. Take it away.
Thank you very much, Amin, and thank you all for coming. It's a pleasure to give this talk in the Cluster Algebra Seminar at the Isaac Newton Institute. Originally, I had hoped to be there in person with all of you, but I'm nonetheless happy to be able to share with those of you who are there in person and also the Zoom audience. So I'm glad that, and also to future people watching this on video. So I'm going to be talking about two different papers that are both joint work with Nick Ovenhouse and Sylvester Zhang. One paper was from February of this year, and I think some of you have seen me talk about that previously. And then the main thing I'll be talking about today is based on our paper that just appeared last month. And my slides should be available in the chat or at this webpage, which unfortunately is less clickable than the chat window. So to begin the story, the topic is of course about cluster algebras, but given this is the cluster algebra seminar, I'm not gonna spend much time defining them for you, just having this one slide reminding you that they're built out of these binomial exchange relations. And the setting that I'll be focusing on today is cluster algebras from surfaces. So with that in mind, let me spend a few moments talking about Teichmüller and decorated Teichmüller space and the relation from hyperbolic geometry. So our starting point is a smooth oriented surface, which possibly has boundary and genus. And then there's a collection of marked points on this surface. The marked points could either be on boundary components or on the interior of S, in which they would be called punctures. And roughly speaking, the Teichmüller space of such a surface is the hyperbolic structures up to isotopy, i.e. up to wiggling, two curves would be equivalent. More formally, I would say that Teichmüller space is the quotient of the character variety. So we take the fundamental group of the surface with all of its features, its holes, its boundaries, the punctures, and map that into PSL2R, i.e. 2x2 matrices. And then we also mod out by an action by such matrices. And basically that's picking a hyperbolic metric on the space. And then Penner took Teichmüller space and decorated it using these marked points by picking what's called a Horner cycle at each marked point. And so that's like picking a positive real number that basically corresponds to the radius or the length of that Horner cycle. And by picking that structure, you get actual hyperbolic lengths of arcs between the Horner cycles. So I'll explain that in more detail in just a moment. So for those who haven't seen it before, I'll be focusing mostly on the Poincare disk model, which has a very specific hyperbolic metric. And what that metric basically says is we have this polygon or circle, and the points of the vertices of the polygon are cusps that are infinitely far away from the center of the polygon. And as you get closer to this boundary circle, it's like the Arctic Circle, it gets really cold. And so it ends up being harder to move. So a geodesic on such a Poincare disk ends up looking like an arc segment as opposed to a straight line, where you try to veer towards the center instead of going straight where you'd be closer to the boundary. And then you can build these two Hoare cycles that I alluded to before. And because of the way the hyperbolic cosine and hyperbolic sine are defined, it makes sense to take an exponential of that length divided by 2. And if we didn't involve the Hoare cycles, this length of delta will be infinite. So it's only by these decorations that we get these nice real numbers to work with. So that's decorated Teichmuller space for a polygon. And using these, what are called lambda lengths, those exponentials of those hyperbolic lengths, they satisfy this Ptolemy exchange relation. So here I've drawn the quadrilateral as if it's Euclidean, but you really should think of this as hyperbolic lengths. But just symbolically, as you flip the diagonal E to the diagonal F in the quadrilateral, it induces this algebraic relation among the lambda lengths. So lambda, the product of the two lambda lengths of the crossing diagonals, is equal to the sum of the product of the lambda lengths of opposite sides. And since we'll be saying lambda lengths throughout this talk, I'll just abbreviate this as EF is AC plus BD. So some other structural theorems I want to remind you of from cluster algebra theory. So from the very beginning of cluster algebras, Fomin and Zelvinsky showed that even though these binomial exchange relations look like they only induce rational functions, they're indeed Laurent polynomials where the denominator is a single monomial. But then it took another decade and a half for the positivity conjecture to be proven, where when you write this out as a Laurent polynomial, that the numerator of any cluster variable does in fact involve only positive, or more specifically non-negative, integer coefficients. But if we focus on the special case of cluster algebras from surfaces, there was a combinatorial model and positivity that came before the general theorem. So going back to 2006, Fomin, Shapiro, Thurston showed that if you have any Riemann surface with marked points, you can give it a cluster algebraic structure where you pick your hyperbolic metric and Hoare cycles, so that for a given fixed triangulation, let's just call the lambda lengths of those initial arcs as x1 through xn. And then as you do the quadrilateral flips, you get other arcs between the corresponding Hoare cycles, and those will get expansions in terms of the original x1 through xn, and they end up being all Laurent polynomials based on applying the cluster mutation rules again and again. And so from the perspective of hyperbolic geometry, these Laurent expansions are really just the lambda lengths of these arcs from the point of view of Penner's decorated Teichmuller space. So going back to work of Ralph Schiffler in 2006, and even unpublished work of Carroll and Price before that, there was this combinatorial model involving t-paths for the specific case of a cluster algebra from a polygon. And these are cluster algebras of type AN as well. And I'll say more detail about these in a few moments, but just for this slide, let me emphasize that you get combinatorial expansions of the Laurent expansion by drawing paths from vertex 2 to vertex 5. And I'll just focus on the middle example. You have a path that goes from 2 to 1, then 1 to 3, then 3 to 4, then 4 to 1 and 1 to 5, and alternating what contribution goes in the numerator and what goes in the denominator gives you a monomial, a Laurent monomial, and that is just one term in this t-path expansion that it is equal to the Laurent polynomial expansion for that given cluster variable and lambda length. In 2007, Ralph Schiffler working with Hugh Thomas, and then Ralph Schiffler as a solo paper, extending this to other unpunctured surfaces, and then also with principal coefficients. And just an example of what these t-paths can look like for other unpunctured surfaces, here we have the next basic example of an annulus. And as you do the quadrilateral flip, you get arcs that spiral more and more around the boundary in the middle. And so it gets more and more gnarly. And so you need a t-path formula where your path is homotopic to this specific winding arc. And so you can definitely work with such a formula, but topologically it gets harder and harder to work with. So in 2008, I worked with Ralph Schiffler to give a bijection between these t-path formulas and snake graph formulas. And I'll say more about snake graphs later on, but just as suffice it to say that if you look at these perfect matchings of these deterministically built graphs, it gives a different generating function for the cluster variable formulas. And then in 2009, work with Schiffler and Williams, Lauren Williams, extended this to surfaces with or without punctures. But for today's talk, I won't really have to focus on the punctured cases. Any questions so far?
No.
So I want to switch gears now and talk about superalgebras and superspaces. So a superalgebra is a Z2 graded algebra. So there's even and odd parts. Even elements commute just like the ordinary cluster algebraic case we were talking about. And even parts even commute with odd parts, but the odd elements anti-commute with one another. So in particular, if I let the xi's be even parts and the theta i's be odd parts, we get that xi xj is still xj xi. Same thing for xi theta j, but theta I theta j is the negative of reversing the order. And in particular, when you write out odd elements, they have to be square free, since theta I squared is always 0 in a superalgebra. And you can look at monomials with an even number of odd elements that will still be an even element, and then monomials with an odd number of square-free odd elements, even if it's more than one, will also be an odd element. So as an example, here is an example of an even element, and here is an example of an odd element. So in this context, you can replace the PSL2R that was our way of defining Teichmüller space using the character variety point of view, and replace it with OSP12, which is a 3x3 matrix with one even element and two odd elements. And Penner and Zetlin showed that there's a definition of a super Teichmüller space for any surface, again, using its fundamental group. And similar to the bosonic case, i.e. the even case, you can get a decorated super Teichmüller space by endowing each marked point with a horocycle. And this leads us to the definition of a super lambda length. But unlike the bosonic case, it's not enough to just have the super lambda lengths. There needs to be additional invariants that accommodate this extra degree of freedom coming from the odd dimension. And so for every triangle, rather than there just being lambda lengths attached to the edges of the triangle, there's also an odd variable that's attached to the triangle itself. And so we'll think of that as a point in the center of the triangle, or the index by the face of that triangle. There's also an extra feature of super tight Miller space, which are spin structures on the surface. So Simotsani and Reshetikin think of spin structures as isomorphism classes of Castellane orientations in terms of fact graphs. But another way to think about this that's dual to that formulation is orienting the triangulation of the surface itself. So here, epsilon A, epsilon B, and epsilon C are meant to represent an orientation of those given edges, like an arrow, and their negation is just reversal of that arrow. And there's also a mu invariant. Here it's indexed by theta, and you can negate that mu invariant algebraically as well. And so if you reverse the orientation of all three edges and negate the mu invariant, that will be an equivalent spin structure, or really the same spin structure up to equivalence. So with those spin structures in mind, we can define a super Ptolemy relation, or just the Ptolemy transformation, given as follows. So imagine we have 4 cycles on this quadrilateral, so that we have super lambda lengths for each of these 5 arcs. And then you flip E to F, but instead of thinking it as flipping, since it has an orientation, we instead really think of it as 90-degree rotation. So it really, when we go from E to F, we're really rotating through edge B. And we'll see why that's relevant in just a few minutes. And with that in mind, you get this algebraic relation that EF is not just AC plus BD, but the product involving mu invariance and a square root of the cross ratio. And you also get new mu invariance based on the new triangulation. And notice there's a sign that shows up, so that being on the left or the right of the oriented edge matters. So that's a super Ptolemy relation. And we can rewrite this because of the algebraic nature of the cross ratio and the way that the mu invariant shows up. We can rewrite this in this as a 3-term relation. And we can also recover that the product of sigma theta in this order, so notice that's the right side of the oriented edge followed by the left side of the oriented edge, is the same as the product of the mu invariance of the resulting quadrilateral after the flip. And unlike the ordinary case, super Ptolemy moves are not involutions. In particular, you negate this edge that you rotated through, this edge labeled as B. But if you do this 8 times in a row, you do get back to where you started. And in our case, when these are boundary edges, we will not really care what the orientation on a boundary edge is. So the even degree elements of a super lambda length, it's not too hard to see these exactly recover the ordinary lambda lengths in the decorated Tickler space. And also, if you flip the same diagonal twice, even though it's not the same exact mu invariant and triangulation as an orientation up to this equivalence relation we mentioned, it is the same spin structure. So in that sense, we can say that flipping twice does give you back the same spin structure and triangulation. So with all that in mind, let's do an example. So let's start with the, oh, sorry, question?
Can you show the previous slide?
Yeah.
Yeah, so what about the bottom triangle, the triangle which contains sigma? So you have one edge, this horizontal edge change orientation. So it means that in bottom triangle spin structure changed, right?
Yeah, let me say a little bit more. So when you flip, do the first flip to flip the edge between theta and sigma into the edge between theta prime and sigma prime, the only orientation that changes is the one on edge B. And then when we do a flip again, the only edge that changes orientation is edge A. So at this point, the mu invariant, really it's sigma, I should call it sigma double prime, but if you do the calculation, you'll see that sigma double prime really agrees with the original sigma. But the top triangle, this really is the negation of what you started with. However, you can do a orientation flip only on the top triangle without changing the bottom triangle at all.
No, I'm asking about, you have arrow on the horizontal.
Yes.
It change, well, the direction of arrows flipped.
The direction of D and C are the same,
yeah,
as they were.
I mean horizontal arrow flipped, right?
That's right, yeah, once you do this twice. Yeah.
Then maybe I misunderstood you, but my understanding was that the orientation of all edges are part of the picture, right? So
that's correct.
So if you consider the bottom triangle, so it's not the same as bottom triangle on the right is not the same as triangle on the left, right? Because
right. So yes, that's right. So let me annotate for a moment. So this, right. So this exact orientation is not the same as this one. However, once you do this move, this becomes a plus, this becomes a plus, this goes the other direction now, and this becomes a plus. And so at that point, they do agree on the nose. And that also is why the bottom ends up being the same, only because you flipped the horizontal edge.
Yeah, thank you.
Sure. Other questions? Okay, so I want to do this example of the pentagon. So let's start with this specific orientation, just to make the bookkeeping precise. And we're going to flip X1, the edge between 1 and 3. And we're going to basically rotate it 90 degrees through edge D. So that's why, and the boundary edges are ignored, but I'll just mention their orientation when they're negated just for bookkeeping purposes. And so we want to understand what are the super lambda lengths from 2 to 4, 2 to 5, and 3 to 5. And so we first flip X1. And so that negates the edge D, but that doesn't directly affect what we're doing. I just want to note it for bookkeeping purposes. And now we have an edge X3, and its super lambda length by the Ptolemy exchange relation is given like so. And we also get 2 new mu invariants. And there's a minus and a plus accordingly based on where they sit relative to the oriented edge X3. So that's one flip. And we're now going to do the same super Ptolemy exchange to X2. So again, we rotated through edge C, which gets negated. And now we have edge X4, which I'll write in terms of the second triangulation. So that involves X3, theta 5. But theta 5 and X3, we just saw had expressions in terms of the original triangulation and mu invariance. So plugging that in, it becomes a little more complicated. But after doing some simplifications and noticing that when you do a square root of a mu invariant and multiply it by a mu invariant, you get cancellations, we get the following expansion. And so a natural question is, if we now flip x3 to get to x5, what do we expect to get? So before I answer that question, let me talk about the more general case. So in a cluster algebra, we expect all cluster variables to be positive Laurent polynomials in the initial cluster. What do we hope for in the super lambda length case? Especially because we have anti-commuting variables involved. So the answer is we can't quite get Laurentness, but we get something like Laurentness involving square-free expressions of the theta i's, which have to be in the numerator. Those are the odd elements. And at most square roots of the even elements, which can be in the numerator or the denominator. And then you get Laurent-like expressions involving these alphabets. Furthermore, there's a specific orientation of a triangulation and a specific ordering for multiplying odd variables together, which we call the positive ordering, which will ensure that in the polygon case, all of these expansions are indeed positive. So let me continue with the example. If we flip x3 to x5, then we get theta 4 and theta 7 end up being these two expressions, which theta 7 can then be simplified using our formulas for x3 and x4 into this easier to use expression. And then x5, after a bunch of algebra, ends up being this more simple expansion. So it's even simpler than it was for x4. Just to remind you, x4 looks like the following. So x5 is now simpler. And if you continue, you'll see that flipping x4 and x5, you recover x1 and x2 on the nose. So even in the super decorated Teichmuller point of view, we get the pentagon relation for these super lambda lengths. And also, while it's not immediately obvious, the expansions of super lambda lengths themselves don't depend on whether the arc x4 is oriented from 2 to 5 or 5 to 2. However, when we pick the spin structure of the initial triangulation, that will determine the signs of these expansions. So we're specifically picking a spin structure and orientation so that all these expansions are only positive. And notice we also had to say that we're multiplying theta 2 then theta 3. If we did theta 3, theta 2, for example, this would also give us a negative sign here. Any questions about the pentagon example? All right, so I want to now talk about the more general polygon case. So in the classical situation, these were Scheffler's t-paths. So you think of the triangulation of the polygon as a network of vertices and edges, and you want to have a path from I to j so that no edge is used twice in a row. There's an odd number of edges. The even numbered edges cross the diagonal I to j, and the intersections move closer and closer from I to j as you continue along the t-path. And you then give the t-path a weight by putting the odd indexed edges in the numerator, technically they're lambda lengths, and then the even index edges in the denominator. And then by looking at the sum over all t-paths, this generating function of their weights is exactly the lambda length of the arc from I to j. So here again is the example from 2 to 5 we saw earlier, and you see that you exactly get the weights that you expected. So the result of our first joint paper with Nick and Sylvester was a super T-path formula for the super decorated Tickler space case. And instead of reminding you of that, I'm going to talk about a related cousin of this, twisted super T-paths that we discussed in our more recent paper. And eventually we want to get to a snake graph interpretation, but twisted super T-paths are a related deformation of T-paths that are more closely related to the snake graphs. So that's why I want to mention these here. So if you're familiar with our previous paper, the setup is quite similar. We only allow triangulations where we have the longest arc crossing all internal diagonals. So for instance, a hexagon like this with this triangulation would not be allowed because instead we would have to pick a specific arc that we'd be focusing on. And then we would say that the triangulation that we have in mind is really only the triangles that are crossed by that red arc. So we don't really lose any possible formulas from this for the super lambda lengths, but this is a difference that we have to emphasize in this case. So secondly, we are going to focus only on triangles that have boundary edges. And again, there's no loss in what arcs we can handle that way. So consider the longest arc from A to B. It's going to look like this, or sometimes we go from bottom to top instead. And we want to first define a canonical fan decomposition. So for that, we consider the fan centers by intersecting the arc from A to B with all the internal triangles. And we highlight when we get smaller triangles instead of quadrilaterals. And those end up being the fan centers. And these subtriangulations end up being fan segments. And we end up defining a default orientation on the interior diagonals using this fan decomposition. So in particular, for every given fan segment, we direct the orientation away from the fan centers. But then there's this ambiguity on the edges that connect fan centers. So C1 to C2, then C2 to C3. So we orient that in a zigzagging fashion. So let me just draw for a moment. So notice we have C1 goes to C2, then C2 to C3, C3 to C4, etc. And we also want to define a positive ordering. How do you multiply these mu invariants together to preserve positivity? It's a very simple, it's a compact definition, but it's a funny one if you haven't seen it before. First, for every single fan segment, we orient them counterclockwise around its fan center. So delta 2 would become before delta 1, but then we alternate as we go from bottom to top as we cross the fans. So for instance, gamma 1 comes before gamma 2, comes before gamma 3, again going counterclockwise around the fan center. But this would all come before the fan center involving the deltas. But then as we go up further, everything would come before the betas. That would be the next fan center. And then finally the top would come before everything that came below it. So you get this ordering, which if you don't build it from bottom to top and alternate looks funny, but it really is this zigzagging fashion. So with all these definitions, In our original paper, we defined the auxiliary graph connecting fan centers to the centers of the triangles. In this case, I'm going to define something called the twisted auxiliary graph, which uses the complement edges. So instead of connecting the fan centers, we, for every triangle, use the other two edges. And we denote them in thick blue and light cyan, depending on whether that edge in question is closer to edge vertex A or closer to vertex B. And then finally, we have all the fan centers are connected to one another along a spine that allows you to teleport from any center to another. Sorry, not a fan center, but a face center, a center of a triangle. And the resulting graph is called the twisted auxiliary graph. And so we're going to build twisted super t-paths on this twisted auxiliary graph. So the first four axioms are exactly the same as Schiffler's, but then we're going to consider teleportation to be even steps, and those cross AB, even though they technically look like they're going along the edge AB. And then the other edges, these blue and cyan edges, are going to be sigma edges, and those must be odd indexed. And we also want, just like before, that as you do these moves, you get closer and closer to the bottom of the end of the arc A to B. And if you are familiar with our original paper where we talked about super t-paths, these definitions are quite similar, except we reverse the role of what's even indexed and what's odd indexed. And that's to make this match up nicer with the snake graph formulas that we'll have in a little bit. So we let T twiddle denote the set of all twisted super t-paths on this twisted auxiliary graph. And every ordinary t-path is in fact an example of a twisted super t-path. So I know this definition is a little heavy, so let me do an example. Well, before I do that, let me define the weights. So it's going to be very similar to what we saw before. For diagonals in the original triangulation, they're in the numerator denominator as lambda lengths, respectively, technically super lambda lengths. But then if it's a tau edge teleportation, it's unweighted. And if it's a sigma edge, which are odd index, then it's a mu invariant times this square root, where it's adjacent over opposite. And the twisted super t-path has a weight given as the product of all those, where this product is taken since it involves mu invariance using the positive ordering, regardless of combinatorially which mu invariants show up in what order. So the positive ordering definition overrides the combinatorial ordering for the mu invariance. All right, so with all this in mind, let's do an example. So we get this theorem that the super lambda lengths are indeed the generating function of the twisted super t-paths. And we can actually get this for any arbitrary orientation up to changing the orientation on boundary edges, which we don't really care about. But sometimes you have to negate a mu invariant, so that's why you would get possible signs in the expansion. All right, so that was a lot. I was foreshadowing this example a couple of times. Let me actually get to it now. So imagine you're considering the arc that goes from the corner of x4 and x5 to the corner of x1 and x2. And so there's all the ordinary t-paths that you would be used to. I'll just draw one for art for example's sake. So you might do something like this, and that would just be an ordinary t-path. But the twisted super t-paths that are not ordinary will give contributions involving mu invariance. So let's break down this example. So here we go along x5. Then we go along x7, and that contributes the x5 in the numerator, and then the x7 in the denominator. And then we have a sigma step that has x3 and x8 as adjacent over x9 as the opposite. So that's an x3, x8 divided by square root of x9. And then we do this teleportation step. And then we finally do one more sigma step that would be square root of x1, x2 divided by the square root of x9. And the square roots of x9 cancel one another to give us this x9. Sorry, not cancel, but combine to give you this x9 with no square root in the denominator. So any questions about this first monomial? Hopefully this example here is clear. And then I'm not going to go through them all, but here are some other examples of super twisted t-paths. So here you, again, start in the same corner and go along this edge, then this middle edge. And then it's only at the very end that you would do sigma edge, teleportation, sigma edge. And then I'll leave it to you to check this one on the bottom. There's 9 more examples, which I'll let you look more closely at your leisure. Most of them, notice, involve only a single teleportation. So it's really a sigma edge and a tau edge, and then a sigma edge, and then some ordinary t-path contributions. I want to focus on this bottom one here, because this is the only example in this hexagon case where you have teleportation twice. And because of that, you actually get 4 mu invariants instead of just 2. So that's an example of the twisted super t-path expansion for this specific super lambda length. So we'd have the 9 elements involving these mu invariants, and then 5 others from the ordinary t-path point of view. So the main result of our new paper is a snake graph formulation that also gives you a combinatorial interpretation of these super lambda lengths. So just to remind you, a snake graph is a planar graph with square tiles connected to the top or right of the previous tile. So you can build a word out of it using this alphabet of right and ebb steps. And so as an example, if you had this particular triangulation and you had this dotted arc is the arc that we want to build the super lambda length of, we could build a snake graph quadrilateral by quadrilateral so that we see the mu invariants as the corners of the tiles. And every 2 quadrilaterals in a row is going to share a specific boundary edge. So for instance, this blue quadrilateral shares edge y1 with this red quadrilateral. So that's the edge that we use to glue the 2 tiles to one another. The tile involving theta 2 and theta 3 shares edge y2 with the tile involving theta 3 and theta 4. So we glue again to the right, and then we glue to the up using edge y3, and then we glue to the right again using edge y4. And we could also involve edge weights, but since it would make the diagram a little cluttered, I didn't include that. But that would be how you would build super snake graph out of such a triangulation, where you have not just the edge weights, but also mu invariance. So one surprise from this work is that instead of it getting a dimer interpretation, a perfect matching interpretation, you actually get a double dimer interpretation if you want to build the super lambda lengths. So here we're going to let blue edges be double dimers. So in particular, even though I draw it as a single blue edge, this is really these two edges together in disguise. But then when we draw the orange wavy edges, that really are single edges. And that's part of a cycle. And it's provable since every vertex of a double dimer cover has to be incident to exactly two such edges, that it's double dimer edges and cycles. And we give a weight of a double dimer cover in a non-trivial way where you involve square roots of the edges that are involved, but then you also have to involve the mu invariance. And the way we invoke the mu invariance is every cycle in a sub-snake graph has a first triangle with a mu invariant and a last triangle with a mu invariant. And so that ends up being a contribution from a given cycle. And if we add a double dimer cover with multiple cycles, we would get multiple mu invariants rather than just two. So for instance, that there were two cycles. So for instance, if there was a wavy cycle here instead, then that would contribute a theta 5 and a theta 6 as an example. And so using this weighting, our main theorem of our more recent paper is that when you have F is the longest edge of a given triangulation, then the super lambda length is the generating function over double dimer covers, where you have to use a crossing monomial, just like in earlier work with Schiffler and Williams. And there you just do the product of the edges crossed by the arc as normal, but then the weights of the even decomposes into an even and odd part. The even part is the weights of the edges with multiplicity, but every individual edge is taken with the square root. And then again, for every cycle, it contributes theta I, theta j, based on the first and last triangles in that cycle. So that's our main result.
Greg,
Yeah, please.
So this theorem is about triangulation of polygons or surfaces also?
Yeah, sorry, this is for polygons.
Okay. And kind of, I tortured Nick at some point and he told me the formula from your first paper and then did some kind of calculation. It seems that like in simple cases, it seems that in examples you can renormalize status multiplying it by some roots of even variables such that they will disappear at final formula, like totally. In small examples.
Yes.
I'm not sure if it's true in general case or.
Yeah, that's correct. No, that it's true in general for the polygons. Let me back up for a moment. So if I focus on this examples involving the twisted super T paths, another way of stating what you were just asking about is that when you do a combination of, let me put it in black. When you do a combination of a sigma step, which has to be immediately followed by a teleportation tau edge, followed by another sigma step, you can think of these three steps together as one unit. And if you give a different weighting that basically is the weight of that unit, that's going to involve two mu invariants. And in theory, it involves these square roots, but you could, again, renormalize so that this didn't really involve square roots. So that's essentially what's happening with that normalization that Nick was talking to you about.
Thanks.
Sure. And as I said, in this last example, this is the only one where you basically have two of those in a row. So it's basically one super step, an ordinary step along the middle edge, and then another super step. Other questions? And in terms of the snake graph formula, you can also think of these cycles as being related to those super steps. So you could do a renormalization. Although when we tried to write it that way, it actually did not look it nice, because once you do the renormalization, then some other things broke. So
it was really my question. What is Brock? So because why don't do renormalization like from the very beginning and then get rid of the...
So when you write the formula for the mu invariants, when you do the renormalization, then the mu invariants don't look as nice.
Meaning, okay.
Yeah, it's hard to say right now, but I'll come back to that in a few moments.
Okay, thanks.
So just to be concrete with the Pentagon example again, instead of the super t-paths or twisted super t-paths, we would get these ordinary double dimer covers. So where every double dimer looks like a perfect matching because it's two edges simultaneous. And so even though there's really square roots, it's squares of the square roots. So it just looks like the ordinary formula. But then when you involve cycles, then you do see these mu invariants and square roots showing up. And I just want to emphasize that this last one involves theta 1 and theta 3. The theta 2s in the middle are not relevant for the formula. So what about odd variables? So you can start with an arc gamma like before and choose a triangle and its mu invariant. But we have to choose only the mu invariants where one of the sides is a boundary and the other side is this longest arc. That's just like one restriction we have at the moment. But with that restriction in mind, we can express the mu invariant in terms of the initial triangulation. So recall that the snake graphs are labeled with the odd variables, like I wrote here. And there's a toggle involution that I have to define for you. So let theta n be the label of the upper right last tile. So in this case, it's theta 6. And we want to just toggle a monomial by adding or removing that. And that will turn an even superelement into an odd superelement because it adds or decreases the number of odd elements by exactly 1. So for instance, the toggle of theta 1, theta 2 will be a product of 3 elements, but the toggle of theta 4, theta 6 would just be a single element. And so with that in mind, the formula for odd variables can be written in this form. It's a little more complicated than we would have wanted, but this is the simplest and most compact we could get it. So the left-hand side is the mu invariant multiplied by the square root of 2 super lambda lengths. So D in general would also be a super lambda length that's not in the original triangulation. But then on the right-hand side, E and B are in the original triangulation, and then you're summing over a subset of the double dimer covers. And so every other weight on the right-hand side is something that involves the original triangulation. But instead of using all double dimer covers, it's only those that use the top edge of the last tile, but you can use it once or twice. And just as a fine print for experts, this is really assuming that the polygon in question has an odd number of triangles. If it had an even number, then you just change this use of the word top to right, just by symmetry of the snake graph. So what this is really saying is, if you look at the formula for super lambda lengths, which we already discussed, expanded that out in the initial triangulation, took its square root and multiplied it by the expansion in terms of the mu invariant, and then there'd be some cancellation because mu invariance might, the same mu invariant might show up in the square root of df and this, so that would you take cancellation until it's square free, that would involve the equal the expansion on the right hand side. So as a small example, let's take the mu invariant for the triangle at the top in this particular pentagon. You would build all the double dimer covers that use the top edge labeled as C. You would build the generating function with those weights. You would do the toggle involution, which would include or not include a theta 3. And then you would multiply by square root of y over square root of c. And that in turn is equivalent to what you would get if you expanded out the square root of a times the square root of gamma, the edge from this corner to that corner, times the mu invariant. And here, as an answer to your question, Misha, if we did the renormalization from the beginning, then this would be more complicated.
It will be more complicated, but it will be square root free.
Right, yeah.
Okay.
All right, so I'm close to time, but I hope you'll bear with me for a few minutes for me to just sketch the proof and then tell you some applications. So first of all, looking at the top right corner of the last tile, we see that there are three cases. Either we use the top edge twice, the right edge twice, or each of them exactly once. And so we can decompose the set of double dimer covers into these three mutually exclusive sets. And this mimics the three terms in the super Ptolemy exchange relation. And so in particular, the strategy of the proof is to show that each of these three terms are really these three separate generating functions. But the complication is that we do this proof by induction on the number of tiles in the snake graph, which is equivalent to the number of triangles in the polygon. But since the formula for super lambda lengths involves mu invariance, and the formula for mu invariance involves super lambda lengths, we must inductively prove them together in this double helix fashion simultaneously. But as you do this, the inductive steps really do mimic the recursion formulas you'd expect from double dimers. So just as one small example, if you looked at all the double dimer covers that use the top and right edge exactly once, it could be the end of a self-contained cycle on the last tile, or the end of a longer cycle. And you can think of that as double dimer covers on the graph with one less tile, like not using the very last tile, but having to use the right edge once or twice. So let me talk about some applications. Let me remind you, in the ordinary dimer case, that there's this distributive lattice structure on dimer covers on a bipartite graph that is mimicked by taking a minimal matching and twisting two vertical edges into two horizontal edges, or vice versa. And you can also think of this as the lower order ideals in a fence post set that corresponds to this snake graph where it zigzags when the snake graph goes straight and goes straight when the snake graph zigzags. And because this is a poset isomorphism to lower order ideals, that shows that this really is a distributive lattice. So a question that came up from Bruce Sagan and others when we gave the original talk was, do we have a lattice structure, and do we know if it's distributive for the super t-paths? And the answer was not clear, but because we now know that they're really equivalent to double dimers on snake graphs, we do indeed have the lattice structure that we want. And it is in fact distributive because you can mimic it by fence poset cross a chain and its lower order ideals. So let me just mention that the meaning of this is that instead of flipping directly from a double dimer cover to another one, there's this halfway point where you get a cycle. And you can think of that as you flip edge the face one once and then twice. And so this is indeed isomorphic to the lower order ideals of the fence poset cross two chain. The last thing I want to mention is what happens in the annulus case. So if you have one marked point on both boundary and mutate periodically, we get what we call super Fibonacci numbers. So first of all, we have to make sure that the spin structure is well behaved. And in fact, by doing this specific sequence of flips, you get the same spin structure up to equivalence, except the boundary might be negated, but that's fine for our purposes. And so you get the same product of mu invariants are equivalent over and over again. So we just simplify that, just calling it epsilon. And so you get the super Ptolemy exchange relation is this specific relation over and over again. And so we get unifying recurrence, which looks like the Kronecker quiver recurrence, except with this extra Zm minus 1 epsilon term. And thus we get a super snake graph with alternating mu invariants. And these ZMs are indeed the double dimer partition functions for such snake graphs up to this initialization. And if you're familiar with the ordinary snake graph case, you won't be surprised to know that the even parts are every other Fibonacci number, but the odd parts are this fun-looking sum of binomial coefficients. And if just for concreteness, this is what they would look like as you go in the sequence. You could also ask what happens if you look at the double dimer partition functions for super snake graphs with an even number of tiles instead of an odd number. And indeed, that'll give you the odd index Fibonacci numbers instead, plus these extra coefficients involving epsilon. And altogether, this gives you a certain nice sequence in the OEIS. So open problems are, can we get super lambda length interpretations of these other double dimer partition functions? We expect there are peripheral arcs in an annulus rather than the bridging arcs, but this would involve self-crossings. And it's unclear how to get that in the super Teichmuller space case, because we only have quadrilateral flips to work with. We also are looking at super Markov numbers, which have the super Fibonacci numbers as a special case if you let z equal 1. And last but not least, what happens now that we have snake graphs? Can you get other surfaces? And could you get super analogs of skein relations, which would give us more flexibility than just doing the diagonal flips? So thank you again for listening. And again, this can be found on my website. The slides can be found here or in the chat, or you can look at the archive paper.
Thank you very much, Greg, for the nice talk. In-person participant, if they have questions.
I asked already many, but may I ask one more? May I ask one more?
Yes,
By
yes.
me?
This transformation in, I guess, in the original pen are the invariant under this OSP form, like which is Q-symmetric with respect to even variables and sort of symmetric with respect to odd, right? Quadratic with respect to odd.
Mhm.
Is it true here also that there you have some invariant form?
We don't use the invariant form directly, but since we're using Penner-Zetlin, I think it's there implicitly. Let me just scroll back to this definition. Yeah, so it should be implicitly in what's done in Penner-Zetlin using this OSP 1.2. But we don't use it explicitly, so
No, well, it's sort of different. It's
oh, it's different. Okay.
it's like what replaced Goldman bracket in? So OSP is sort of how it's called.
So you're asking for the analog of the Poisson bracket?
Yeah, correct. Yeah.
This is something we haven't thought of at all. I'm not sure.
Okay. Okay. Thanks.
Sure. I think I see Nathan's question first. I'm trying to understand what combinatorial object a double dimer cover. Yeah. So you can think of it as either a product of perfect matchings, but then when you think about, sometimes that would create a cycle, and whether it's a cycle which would like involve a blue, red edge, like edge 1 from the first perfect matching, edge 2 from the second, or the reverse. We just think of it as a cycle. So I think the answer to your question is, yeah. Does that help answer your question, Nathan?
Yeah, so really if two different unions of perfect matchings give the same edges and cycles, then they're the same thing.
Yeah.
Okay, thank you.
Yeah, in a lot of double dimer theory, a cycle would contribute a 2 for this reason. In our case, it doesn't contribute a 2, it contributes an epsilon, or more generally, the product of 2 mu invariants. I also see Ralph's question. Oh, sorry. Yes, the same answer. Up to that nuance.
So the answer is no, it's not the same as an unordered pair.
Oh, when if you say unordered. Right, I would say it's the same as an unordered pair, but not an ordered pair.
But then shouldn't you just get triangle numbers for the number of dimer covers? Like you got 14 for the
good question. Okay.
instead of 15.
Let me go back to that example. The issue is with the thetas, but I think I can answer your question in that one. Oh, sorry, I'm going the wrong way. Just give me 1 second. Right, so I got the 9 plus, yeah, in fact, let me show it as the whole lattice. Okay, so this lattice of 15 is equivalent to what we were just, so this should be the 15 we were talking about. Yeah, sorry, the 14. So you were asking why there's 14 here instead of 15.
That's right.
Just go at the bottom with 2 cycles. Yeah, it's 2 cycles. Yeah.
Yeah, that's right. So yeah, that collapses to just 1 element rather than 2.
Oh, I see. Okay, thanks.
Thank you for the audience participation that was able to more quickly see it.
Okay, any other questions from the room? I don't see any in the room, and I think there's no more questions in the chat. So let's thank Gregg again. Thank you everyone for joining.